Hey class, I wanted to make this video so that way you could have somebody read to you this summary of the work by Dr. Stozak, professor at Harvard Medical School, about abiogenesis and theories for the origin of complex cellular life. So it says, we know from experiments and observations made in the fields of astronomy, chemistry, geology, and meteorology that the early prebiotic Earth was filled with organic molecules, the building blocks of life. Organic molecules are actually quite common in space. Modern cells separate themselves from the environment with a lipid bilayer. We've learned about these. The problem with modern phospholipids is that they are too good at what they do. They form a nearly impenetrable barrier. Modern cells must use proteins to move molecules across their surface. But life didn't have to start with modern chemicals. The prebiotic environment contained many simple fatty acids. Under a range of pH, meaning acidity levels, they spontaneously, meaning by themselves, form stable vesicles, and they are permeable to small organic molecules, meaning no complex proteins are required to get stuff in. Permeable means allows things to get in, or can cross the barrier. When a vesicle encounters free fatty acids in solution, it will incorporate them. Eating and growth are driven purely by thermodynamics. That's physical laws. When a vesicle grows, it adopts a tubular branched shape, where surface area grows faster than volume, which is easily divided by mechanical forces like waves, currents, and rocks. During mechanical division, none of the contents of the vesicle are lost. So far, with naturally occurring simple fatty acids, we have a vesicle that can spontaneously grow and divide. So what about the genetic material? Again, modern nucleotides are too stable and require complex protein machinery to replicate. The prebiotic environment contained hundreds of types of different nucleotides, not just DNA and RNA, and all it took was one to self-polymerize. Recent experiments have shown that some of these are capable of spontaneous polymerization, such as phosphoramidate DNA. Monomers will base pair with a single-stranded template and self-ligate. They have covalent bond ligation, hydrogen bonds in the middles, and the base pairs between the red and yellow, the green and blue. These stand for the A, T, C's, and G's. They can also polymerize in solution and spontaneously form new templates or extend existing templates. No special sequences are required, it's just chemistry. So far, we have lipid vesicles that can grow and divide and nucleotide polymers that can self-replicate all on their own. But how does it become life? Here's how. Our fatty acid vesicles are permeable to nucleotide monomers but not polymers. When spontaneous polymerization occurs within the vesicle, the polymer is trapped. Floating through the ocean, the polymer containing vesicles will encounter convection currents, such as those set up by hydrothermal vents. Fatty acid vesicles are stable under near boiling conditions. The high temperatures will separate the polymer strands and increase the membrane's permeability to monomers. This is like near a volcanic vent in the ocean. Once the temperature cools, spontaneous polymerization can occur, and the cycle repeats. Here's where it gets cool. The polymer, due to surrounding ions, will increase the osmotic pressure within the vesicle, stretching its membrane. A vesicle with more polymer, through simple thermodynamics, will steal lipids from a vesicle with less polymer. This is the origin of competition. They eat each other. A vesicle that contains a polymer that can replicate faster will grow and divide faster, eventually dominating the population. Let's review. Monomers diffuse into fatty acid vesicles. Monomers spontaneous polymerize and copy any template. Heat strands are separated, increasing membrane permeability to monomer. Pressure on the membrane drives its growth at the expense of nearby vesicles containing less polymer. Vesicles grow into tubular structures. Mechanical forces cause vesicles to divide. Daughter vesicles inherit polymers from the parent vesicle. Polymer sequences that replicate faster will dominate the population, thus beginning evolution. Early genomes were completely random and therefore contained no information. It was their ability to spontaneously replicate irrespective of sequence that drove growth and division of the fatty acid vesicles. Any mutation that increases the rate of polymer replication would be selected for. And as I've shown before, mutation plus natural selection equals increased information. Early beneficial mutations would include change sequence to contain only the most common nucleotides. Don't form secondary structures that block replication. Form sequences that are stable yet separate easily. Form secondary structures that show some enzymatic activity. We know what enzymes are now. Just like RNA, early nucleotides could both store information and function as enzymes. Early polymer enzymes would enhance replication. Use high-energy molecules in the environment near thermal vents to recharge monomers. Synthesize lipids from other molecules in the environment. Modify your lipids so they don't leave your membrane. And that's it. A simple two-component system that spontaneously forms in the prebiotic environment. Can eat, grow, contain information, replicate, and evolve. Simply through thermodynamic, mechanical, and electrical forces. Just chemistry. Think about it.